In this video, we'll examine some of the basic features of path diagrams and see how they can help us to understand the idea of common causes and why we need to include them in multiple regression analyses. Now, another way of visualizing multiple regression is with path diagrams. Path diagrams or path models provide a different perspective on statistical control, particularly when we have a specific idea of how our predictors are related, not only to the outcome, but to each other. We're not going to go too far into this now, but we will spend more time on this idea later. For this discussion, we'll return to our example of two variables, school quality and study hours, as predictors of student grades. In path models, measured variables, things we actually have data on, are represented by rectangles, like our variable for school quality. It's a variable we've actually measured and we have data on it. We have one-headed arrows to show how one variable is predicted to have an effect on another variable. In this case, school quality is predicted to have an influence on our outcome, grades. In path diagrams, we talk about these as paths because it's the path of the effect from school quality to grades. Notice that we use standardized regression coefficients to indicate just how large the effect of school quality is on grades. You don't have to use standardized regression coefficients, and sometimes you can't. But generally, we use standardized betas. In later videos on path analysis, we'll see why we do this. Now, we also have two-headed arrows to indicate that two variables are correlated. They're related to each other, but neither one is seen as a predictor of the other. In this case, our model says that our two predictor variables, school quality and study hours, are correlated. Finally, we have circles and ovals. These reflect variables or effects that we've not actually measured. In this case, R1 is the residual or error when we're predicting grades. Thinking back to our discussion on residuals, you can think of this as those residuals, the difference between the predicted grades based on school quality and study hours and the real observed scores that we have for grades. You can also think of it as representing all of the other factors that influence grades unrelated to school quality and study hours, including things not in our model, maybe the effect of parent education or family income, as well as random error, all rolled into one, this leftover residual effect. Now, this is one type of model for how school quality and study hours may impact grades. But if you think about it, you might also see other models that have a slightly different relationship between the variables. For example, you may look at this and wonder if there's more to that relationship between school quality and study hours than the two simply being correlated with each other. Maybe higher school quality leads to higher levels of studying. Maybe those schools require more effort or inspire students to study more. Either way, that type of relationship wouldn't just be a correlation. School quality would be influencing or causing study hours, just like it's influencing or causing grades. We would need to replace that two-headed arrow with a one-headed directional arrow. If we do, this is what our model looks like. Now, note that I've removed the error term, that R1 circle, in order to simplify the image, but it's still there. Now, this may look similar, but it's a different model in some important ways. We're now saying that it's school quality that leads to or causes students to study more, not the other way around, and not some bidirectional, ambiguous two-way correlation. School quality has an effect on study hours. And notice how this changes how we see the overall effect of study hours. If school quality is having an impact on the level of study hours, then part of the effect that study hours has on grades is in fact due to school quality. Part of the effect of study hours is being driven by school quality. So school quality has two different types of effects on grades. It has what's called a direct effect, seen here in the red arrow. This is that part of the overall effect of school quality that has nothing to do with how many hours a student studies. It's all those other aspects of school quality that are uncorrelated or unrelated to study hours. And then there's this blue two-step indirect effect that school quality has on grades by leading to more studying, which then leads to higher grades. That indirect effect is reflected in both of those blue arrows. You often hear people talk about this sort of indirect effect as mediation, with study hours mediating the effect of school quality on grades. You can think of it as part of that school quality effect flowing through study hours. Now, we'll soon talk about how to analyze and interpret these different models in upcoming videos. But I wanted to introduce this now as part of a foreshadowing of where we're going. And also because it naturally leads us to a key point in an introductory overview of multiple regression. And that's the idea of common causes. In this example, school quality is a common cause of study hours and grades. Notice that it has a causal effect at a directional one-headed arrow on both the outcome, grades, and the other predictor variable, study hours. Consequently, as we just noted, part of the effect of study hours is in fact due to school quality. School quality is driving that effect. It's that driving force behind part of the study hours effect. Now, this is important. If I want to accurately estimate the effect of a predictor in my model, I need to include everything that is a common cause for both that variable and the outcome. In this case, if I wanted to accurately estimate the effect of study hours, I must include school quality in the model as well, because school quality is a common cause of both study hours and our outcome grades. If we don't include school quality in the model, the regression coefficient for study hours will also include some of the effect of school quality. As a result, it will be biased and not give us the true value. In essence, this takes us back to the question of who gets the credit for the overlapping variance in Venn diagrams. Now remember, we're talking about common causes, variables that influence both the outcome and my variable of interest. If something's uncorrelated with my variable of interest, then it's not a common cause, and not including it in my model will have no impact on the effect for my variable of interest. Remember, we previously made this same point when we examined Venn diagrams with uncorrelated predictors. People sometimes lose sight of that and mistakenly think that they must include every variable related to their outcome. But if you have some key variables that you're focusing on, you should try to include common causes for those variables, but you don't need to include all the variables that are uncorrelated with those that are also related to the outcome. So, as this illustrates, path diagrams can help us identify common causes, and understand why we need to statistically control for them. But exactly how we approach this in our analysis will require another video series, okay? So that wraps this up for now, okay? Take care. Bye-bye.